Welcome friends. Today we will be finalizing our discussion on dynamic programming with one last example, and this example that we will be considering today is called as all pairs shortest path problem. What is this problem basically? Now this problem is related to graphs, precisely with directed graphs. So as you can see on the slide, so it's important that a graph has to be weighted, represented by G, which is equal to V and E, which are the vertex set and the edge set. Now with a weight function, so our edge set, which is E, is weighted, okay, based on some weight function. So each edge in our graph, in our directed graph, has some weight associated with it. So the objective is to determine the length of the shortest path between the pairs of vertices in G, between all pairs of vertices in G, to be more precise, because the problem is all pairs shortest path. So given a weighted directed graph, okay, in which each edge has a direction as well as some weight, we need to determine the length of the shortest path, that is the distance between all pairs of vertices in G. It does not mean that the graphs should not have any cycles. What it means is that those cycles should not have zero or negative weights. Some of the basic notions that we'll be using in our algorithm are the weight of a path. As you can see on the slide, the weight of the path, any path between a pair of vertices, is obviously a sequence of vertices V0, V1 and so on and so forth up to the last vertex in the path. The weight of this path is the sum of the weights of its constituent edges, represented by WP, which is basically the sum of the weight of edge Vi minus 1 to Vi. So the weight of the path is simply the sum of the weights of its constituent edges, which is represented as WP is equal to summation of I is equal to 0 to k, which is 0 starts here, to k, which is the last edge, the last node in the path, and we are considering the weight of Vi minus 1 comma Vi. So that is how we are getting associating a weight to a particular path between a pair of nodes. Now the shortest path weight from a pair of vertices U to V, okay, let's consider two vertices U and V. The shortest path weight between these two vertices is considered as the minimum weight if there is a path between U and V. What does this basically mean? It means that let's suppose there are a pair of vertices in our graph, and it is possible that there are multiple paths from from vertex U to vertex V. So there is a possibility in the directed case or in the undirected case as well, that there are multiple paths between a pair of nodes. Now the shortest path weight is basically the minimum weight of all possible paths between a pair of nodes. Okay, now if there does not exist a path between a pair of nodes in our graph, which is in question right now, then the weight of that particular path the shortest path weight between a pair of vertices which does not have any path between them is considered to be infinity. So the shortest path weight between a pair of vertices is the minimum weight of all possible paths between these two pair of vertices. Now if there is no path between them, then we are considering the weight to be equal to infinity, the shortest path weight to be equal to infinity. So we will refer to a path between any two vertices to be the shortest if its weight is the minimum of all the paths that are between those two vertices. So between a pair of vertices, we will refer that a path is shortest if its weight is the minimum of all possible paths between those pair of vertices. So that is what we are basically representing here. Now let's see an example. On the slide you can see we have a directed weighted graph. There are negative weights, there are positive weights, but it is important, as I earlier said, that there should be no cycle with negative or zero weights. In this graph as well, we do not have any negative or zero weights. Now let's consider this pair of vertices. This will consider 4 and 1. Okay. Now what is the weight of the shortest path from 4 to 1, 4 being considered as the source and 1 being considered as the destination. Now if we look at this graph, we have a direct edge from 4 to 1 and it has a weight 2. So this is one path, direct path, 4 to 1. Now is there any other path? So if we go from 4 to 2, from 2 to 3 and then from 3 to 1. This is another path. So, we have an alternative path with weight equal to, this has weight of minus 4 plus 12 plus minus 1. So, it will simply be 12 minus 5, which is equal to 7. So, we have two alternative paths between from 4 to 1, which is 4 and 1 directly with weight 2, and 4 to 2 to 3 to 1 with weight equal to 7, that I just already have calculated here. So, the shortest path would not be the second case, that is marked by green, but the first case, which is this 4 to 1. Similarly, if you observe that for the path from 4 to 2 to 3 to 1, can we find any other path? I guess probably yes, we do have an alternative path, a third path between 4 and 1, and it goes like this. We will go from 4 to 2 and from 2 to 3, okay, from 3 to 4, okay, and from 4 to 1. Okay. This is also a path. Okay. But if we observe, we are considering a cycle here from 4 to 2, 2 to 3 and 3 to 4, then 4 to 1. So, 4 comes twice in this particular path. So, if we remove this cycle, we can shorten the path length, which is directly from 4 to 1. So, whenever there exists a cycle in the path between any two pair of nodes, we can simply remove the cycle and shorten the path. This is one consideration that we might be using later on. Based on these observations, we will try to find a solution using dynamic programming to this problem. So, the formulation would be something like this. Now, let us consider dij superscripted k be the length of the shortest path between a pair of nodes I to j. Okay. So, it is a directed path from I to j, such that now we are representing this dij superscripted k to be the length of the shortest path between from I to j, such that all intermediate vertices on the path, if any, are in the set 1, 2 up to k. So, what does this basically mean? Now, let us consider our earlier example. It means that if we consider this node 4 and this node 2, let us consider 2, 4 and 2. I will write something like this, d 4 comma 2. Now, if I write 0 in the superscript here, if I write 0 in the superscript, it means I am considering the path between 4 and 2 with no intermediate vertices. Okay. I may write d 1 in the superscript 4 comma 2. It means I am considering path from 4 to 2 with intermediate node 1. Okay. So, let us consider both these cases. Is there a path between 4 and 2 with no intermediate vertex in between? Now, if we look at the graph, we can find that there is a direct edge from 4 to 2 with weight equal to minus 4, and obviously this d 4 comma 2 superscripted by 0 is equal to minus 4. Okay. So, this is the length of the shortest path considering no intermediate vertex. Now, what is the length of the shortest path considering the same vertices 4 and 2? So, we need to find a path from 4 to 2 with 1 being, so our set here I in set of intermediate vertices is 1. So, is there a path from 4 to 2 with an intermediate vertex labeled 1? So, yes, there does exist a path between 4 and 2 with vertex 1 in between, okay, as intermediate. So, we will use this notion to build other definitions. So, as you can see on the slide, we are considering d I comma j superscripted by k be the length of the shortest path from I to j, such that all intermediate vertices on the path, if any, if there are any, are in the set 1, 2 and so on up to k. So, the set of intermediate vertices whenever we are specifying k has to be from 1, 2 and so on up to k. So, if the set of intermediate vertices or k is equal to 0, it means the set of intermediate vertices would be 0, or I will say phi, or null in case k is equal to 0. So, I will use this to define all possibilities of dij of k. So, obviously, if k is considered to be 0, then the set of intermediate vertices would be empty, okay. And in that case, the shortest path from I to j, in case there is no intermediate vertex between I and j, considering no intermediate vertex between I and j, would simply the weight of the edge I and from I to j, as I told you in the earlier example. In case there is an edge, if there is no edge, then it will be infinity. Similarly, dij superscripted 1, whatever it be, we need to find that, would be considering the set of intermediate vertices having 1, the lone element. Similarly, dij superscripted 2, we will have to find it, would be such that we consider the set of intermediate vertices having values or elements 1 and 2. Similarly, dij superscripted 3 will have the intermediate set as 1, 2, 3 and so on up to dn of I comma j, which will have the intermediate set equal to the complete set of nodes that are in the graph. So, what we need to basically do is, when we want to find all pairs shortest path, so for any pair of nodes I and j, so if we want to find the shortest path or the length of the shortest path from I to j, we will have to consider, or we have to find dij superscripted by n. So, we will have to consider all intermediate vertices in the process, so all intermediate vertices in the process. So, we will use this notion and try to find the solution to this problem. So, let us suppose we consider this capital D superscripted by k to be the n cross n matrix, where each element indexed by I and j represents this dij superscripted by k. So, for each pair of nodes, so n is the number of nodes, so for each pair of nodes we will use a two-dimensional matrix represented by this capital Dk, wherein each element refers to a pair I and j, okay, from I to j. So, we will have to find, obviously, in order to give a solution to this all pair shortest path problem, we will have to fill in the values for this matrix, this two-dimensional matrix D and of k. Okay. Now, since we are considering this dn of I comma j as the length of the shortest path between I and j, in fact, to be more precise, from I to j, okay, considering all intermediate nodes, we obviously need to find d superscripted by n. So, the final solution would be not to find intermediate dk, where k is 1, 2 or 3, but we need to find d superscripted by n for all nodes in the graph. And in order to build a dynamic programming solution, our solution should be such that it builds on solutions to smaller sub problems. So, we can simply design our sub problems something like this: dk, in order to calculate dk, d to the superscripted by k, for k equal to 1, 2, 3 and so on and so forth, we will use, for example, d1 to compute d2, and use d2 to compute d3, and use d3 to compute d4 and so on and so forth. That is how we will be reusing our previously calculated values, and that is how we will call it a dynamic programming solution to the problem. So, we will see how we will build upon this notion. Now, there are certain observations that we can make on the structure of the path when we are building a dynamic programming solution to our problem, to the current all pair shortest path problem. Now, this structure of the path will obviously have certain features. Now, there are two possibilities whenever we talk about, let's suppose, one is that either whenever we talk about a pair of nodes I and j and we want to find a shortest path from I to j, there is a possibility that none of the nodes belonging to the intermediate set exists on the path between I and j, or from I to j. Or it is also possible that the kth node in that set that we are referring to, as I earlier told you, as you can see on the slide, let's suppose specifying an intermediate set for a pair of nodes, I and j, and an intermediate set I 1 to k. There is a possibility that this k, this node, vertex k is not a vertex on the path. Okay. So, then in that case it is obvious that the shortest such path has length d of I j and k minus 1, means not considering this k, but k minus 1 to be the intermediate set of vertices. Again, now in case k minus 1 is not also on the shortest path, okay, then we need to consider k minus 2, and we can build a recursion for this observation as well. Now, so the first case is, given a set of vertices from 1 to k which are to be considered as intermediate vertices for a pair of nodes I to j, okay, in order to find the shortest path from I to j, there is a possibility that this k node will not exist on the path. So, the length of the shortest path from I to j in that case would be dij superscripted by k minus 1. So, we will building a solution from sub problems. So, in that case, as you can see on the slide, dij of k is equal to dij of k minus 1. Now, in case k is a vertex on the path, let us suppose the other option, the other possibility is that k does exist as an intermediate vertex on the path, then this path between I and j will consist of two subpaths, one from I to k and the other from k to j. It is a simple observation. So, whenever we say that an intermediate vertex k lies on the path from node I to node j, then we can look at this path from I to j being made up of or consist of two subpaths, one from I to k and the other part from k to j. Each subpath here can only contain intermediate vertices 1 to so on and up to k minus 1, because k is being considered as one of the nodes of the subpaths, okay, ending nodes, either the source or the destination. So, the length of the shortest path between I and j in this case would simply be dij, means the length of the shortest path between I and j considering k to be the intermediate set of vertices will be equal to length of the shortest path from I to k considering k minus 1 intermediate vertices plus length of the shortest path from k to j considering k minus 1 intermediate vertices again. So, we will use these two properties, these two possibilities to build our dynamic programming solution. So, the optimal solution would be to use this recurrence as the shortest path between from a node I to a node j considering k intermediate vertices is equal to minimum of dij k minus 1, means not consider in case it is not on the path. This basically means this part here means kth intermediate vertex is not on the path, either this length or the kth intermediate vertex is on the path, and we need to consider the length of the subpaths I to k considering k minus 1 intermediate nodes, and the sum of this I to k path and sum of this k to j path, again considering k minus 1 intermediate nodes. So, there are different implementations of the dynamic programming solution for this all pair shortest path problem. There are numerous there is also one solution through matrix chain multiplication. There is also a top down approach, a bottom up approach, and so on and so forth. So, we will be considering the bottom up approach here. Start building our solution on top of the base cases where we will use the first array to be D0. Now, what is this D0? It means this D0 is basically the length of the shortest paths between all pairs of nodes considering 0 intermediate vertices. So, these will simply be, so if any cell in this array, let us suppose I consider D0 comma 0 superscripted by 0, it means length of the shortest path from node 0 to node 0 with no intermediate vertex. Similarly, for example, D1 comma 2 superscript 0, it means length of the shortest path between from 1 to 2 with no intermediate vertex. Now, as I have told you earlier, this value here is simply equal to the weight of the direct edge from the source to the destination, if there exists any. Now, if there is no direct edge from the source to the destination, then the length is considered as infinity. So, we will build our base case, the matrix D0 superscript by 0, to be equal to the corresponding weights between all pairs of nodes in our graph. Now, we will compute dk from dk minus 1. So, at the current stage, we have d of 0, and we will use this d of 0 to build d of 1. Then we will use this d of 1 to build d of 2, and so on till we reach d of n. So, that is where our final solution will be. But how do we construct this matrix? We will use this relationship that was built earlier. Dij for any pair of nodes or source and destination pair, for I being the source, j being the destination, with k intermediate vertices is equal to minimum of dij superscript by k minus 1 comma dik k minus 1 plus dkj k minus 1. So, it is obvious that starting from d of 0, we will be able, using this relationship, to construct all possible matrices, okay, d1, d2, d3, d4 and so on and so forth till we reach dn, and that will be the final solution to our problem, all pairs shortest path problem. Now, this here is the code snippet which basically implements the Floyd-Warshall's algorithm, which basically uses dynamic programming. Okay. So, the first part here, if you can observe in this algorithm, is that we are initializing this d of I comma j is our matrix that we are maintaining for computing the all pair shortest path lengths, and initially we are setting this to be equal to the weight of the corresponding edges. So, the length of the shortest path between I and j, or source I and destination j, is simply equal to its weight, the edge from I to j. Now, if there is an edge, then it will be the weight. If there is no edge, then it will be infinity. And we are also maintaining an additional array called as the predecessor array, pred of this, with the same dimensions as D array, as our solution array, and we are initializing the values in this predecessor array to be equal to nil, considering that there is no intermediate vertex being currently considered for a pair of nodes I and j. So, for the time being, there is no predecessor before j which needs to be reached from I in order to get a shortest path. So, we are considering no intermediate vertices for the time being, nil. Okay. Now, using this piece of code, which is basically dynamic programming, it uses the previously computed results to generate the further results, or to solve larger problems, smaller sub problems, or generate answers for the larger problems. So, again we use these 3 loops to iterate for all source and destination nodes, and as well as the intermediate nodes that we need to consider. So, this condition here is basically we are checking whether di of the current value of the shortest length between I and j is greater than an intermediate vertex considering k. If that is greater, then we need to replace this value. Okay. So, that is what we are doing here. If an intermediate going through an intermediate vertex yields a smaller weight for a pair of nodes I comma j, then the current weight needs to be replaced, and we are also replacing the predecessor to be equal to k. This array will be used to later on rebuild our path, okay, the path itself. D holds D only holds this array D here, it only holds the length of the shortest path, but if we want to rebuild our path, we will have to use this predecessor array. Okay, if you do not want to regenerate the path, if you only want the lengths, then we do not need to maintain this predecessor array. So we'll see how we'll use this predecessor array to generate our final sequence. Okay. So this is a small piece of code which uses that predecessor array maintained by the earlier algorithm to generate our sequence. So if the predecessor of I comma j is equal to nil, it means there was no intermediate vertex found such that a path from I to j considering that intermediate vertex yielded a shorter length. So we'll simply output I and j edge as itself. So shortest path between I and j in case predecessor is nil is the edge between I and j. So we'll simply output I and j. Now in case it is not nil, then we'll have to generate the path from I to that k and path from that k to that j. So the two subpaths that we were talking about earlier, I to k and k to j. So we'll display that recursively again till we finally find the solution to it. So as an example, let's suppose on the slide you can see, let's suppose we have already run our Floyd-Warshall's algorithm and we have filled in all those values for predecessor array as well as the D array, and the D array gives us the all pair shortest path values, but the path itself, we want to find a path between any pair of nodes. Let's suppose in this example we are given path 2 and path 3. So we'll use this function to display our path, shortest path between 4 and 5. So we are given source 2 and destination 3. Will make a function call path of 2 comma 3. We will search that the predecessor of 2 comma 3 is not equal to nil, and let's suppose for the sake of an example it is 4. So what we'll do is we'll simply make a recursive call from 2 to 4 and 4 to 3. So the first call, this here 2 to 4, will again be made, and let's suppose the predecessor for 2 to 4 is 5. So we'll have to find the path between 2 to 5. Okay, we'll make another call 2 to 5 predecessor, let's suppose it is equal to nil. Now in case there is no element between it, this basically means there is no intermediate vertex between 2 and 5. So for our final path we can display this edge 2 to 5, that's what we'll do. So in our output we have specified one edge to be 2 to 5. Now there are certain remaining function calls or pending function calls that need to be made. 2 is done, so we need to make a call for 5 to 4, and let's suppose we find that the predecessor for 5 to 4 is nil. So there is no intermediate vertex from 5 to 4, so we simply output edge 5 and 4. Similarly 5 is done, so we are still left with 4 and 3. Let's suppose the predecessor is 6, so we'll have to find the path from 4 to 6. Okay, and let's suppose that the predecessor is nil, so we'll output 4 and 6. And finally between 6 and 3, let's suppose the predecessor is between 6 and 3 is also nil, so the output will be 6 and 3, and this is the final path, okay, itself, which was found to be shortest, okay, by the Floyd-Warshall's algorithm. Now this array was maintained intermediately by the Floyd-Warshall's algorithm, and this is how we used it to regenerate our result, besides being able to determine the length of the shortest path, which will be simply in the D array, D of 2 comma 3 will give us the length of the shortest path, okay, and the path itself has been generated from this predecessor array using this function. Now we have already discussed enough examples for dynamic programming. You can practice other problems or other approaches, either top down, bottom up. You may also try the matrix chain multiplication, uses the similar concepts. In the next class we will be starting a new method of solving problems that we call as branch and bound. Okay, it's a little bit different from dynamic programming. That is also another approach of solving certain specific type of problems, certain problems with certain characteristics, and we'll discuss that from our next class onwards. So till then, goodbye and thank you.